Alright, let's look at a situation. Here we have some kind of bar, and it has unit torque. So it's not just a torque at the end or a point torque somewhere in the middle. It's not just applied to one part. It's a unit torque. It's distributed throughout the whole entire length. So we can notate that like this. It's kind of hard to draw, but we can call it that and say that this is our little t because it's distributed as opposed to the point. We do this a little bit differently than we've done other things. So let's go over this. We have that this unit load is 480 pound-inches per inch. Now let's say if this makes sense, these units, we have pound-inches was just torque. And we're talking about unit torque, so it's torque for any given inch. For every inch we have this much torque, essentially. So that ends up just being pounds, which is kind of weird. But that's why we write it in terms of pound-inches per inch. We have length. I'll just draw that on our diagram. That's just 12 feet. I already notice we have feet and inches going on. Unit conversion, I foresee. We have our shear modulus is 11.5 times 10 to the 6 psi. And they give us, I like it when they give us the polar moment of inertia, 17.18 inches to the fourth. First thing that we need to do is derive a formula for our shear strain. And typically it looks like this. I'll start from torque times displacement over 2. And knowing that our phi equals torque times length over g times IP. We plug that in, and our general formula is torque squared times length, 2 times g, our polar moment of inertia. Now, the difference is we don't have a big T anymore. We don't have a point torque. It's distributed throughout the distance. And remember, torque is internal. So essentially, what I need to do is I need to cut it at every location and know what the torque is at that location. Or in other words, a different way of looking at that is just making a little graph. If I were to cut it at the very end here, infinitesimally close to the end, there would be infinitesimally amount of torque. It would approach 0 torque at the very end. So where x equals L here, it's at 0. At here, it's going to be our entire torque over the distance. And it's a linear relationship. This is where x equals 0. Now for each infinitesimal little torque, we have an infinitesimal length as well. We're looking at an infinitesimal piece here, where the length is dx, and our little torque is defined by our equation here. Depending on where we cut, depending on what our x is, that's going to be L minus x times little t. So let's check this out real quick. So when x is L, this equals 0. The whole thing equals 0. And that's what our graph agrees with. When x equals 0, the top equals the total torque times L. We can know the total force here by knowing the distributed times that whole length. That gives us our total torque. You can call it T naught. It just equals little t times L. So that's our maximum torque. But this is what we want to use because this is our internal torque at any given x. So our new equation, we have to sum up all of our little strain energies. This is L minus x times t, and that's all squared, times our new distance, dx, for each of those. We're divided by 2 g IP. Now let's see, does G change while X changes? No, it's the same material everywhere. Does our polar moment of inertia change? Well, that's based on shape, and the shape doesn't change. It's the same diameter. It's not sloping in like a cone. So we can just take all of this bottom part and take it outside of the integral, and that helps us a little bit. Makes it so we can focus on integrating. Okay, I almost forgot to put in our limits of integration. We defined this to be 0 where we start, and this to be L where we end. So that's from 0 to L. 0 to L. And I'm going to FOIL out our square here. L squared times T squared minus 2XLT plus X squared T squared. That should be T squared. And all of that is times dx. Now it's just simple integration in terms of x. So these are the variables that we're looking at. The t is constant, the L is constant. We're just looking at x right now. Alright, L squared, T squared. The integration of a constant is that constant times x minus, we have a constant times x, so we have that constant. The integration of x is x squared over 2. The constant doesn't change, but the integration of x squared is x to the third over 3. And that's from 0 to L. Now I can plug in my limits. I know that 0, since everything has an x in it, is just going to result in 0. So I can just plug L in everywhere I see an x. So I get L to the third T squared minus, these 2's cancel, get L to the third T squared plus T squared L to the third divided by 3. Alright, I'm almost at the point where I can plug in numbers. I have one more step here. Notice that all of these are L to the thirds times T squared. I can cancel these two out, and I'm left with, okay. So this 3 times this 2 is 6 GIP, and that agrees with what was done before. Now I can just plug in my numbers. My T was 480. I could just put in pounds, although in our hearts we know it's still pound inches over inches squared. Our length was 12 feet to the third over 6 times, our G was 11.5 times 10 to the 6 psi. Notice I know I have inches and feet, so there's going to be a unit conversion. Okay, and I have my polar moment of inertia. They give that to me at 17.18 inches to the fourth. So I still have inches and feet here. I want it to be standardized and uniform. So I have 1 foot, 12 inches. I'm trying to cancel out these feet here. This is feet cubed. So in order to cancel that out, I have to do that unit conversion 3 times. So put that in my calculator, and I get an answer of 580.4. So pounds cancels with pounds. Per inch squared times inches to the fourth leaves me with inches squared. This is going to leave me with inches to the third, so this should just be, oh, this is pound squared, so I should have pound inches, which is the units of energy. So we are done.